I look forward to the day in which we can all be together in the same room rather than spread across many countries and in different places. And hopefully that won't be in the too far future. Can everyone see my slides? Let's just see if we can load that. You can see my slides, okay. Okay. Well, good morning, everyone. As I said, think of this session as a gentle introduction. It's early on a Monday morning here. So I'm going to hopefully ease you in gently into what is going to be some quite technical material later on in the week. And as a young man, I used to very much enjoy athletics and running. So you might hear me using some running analogies. So if I use a running analogy to start with, we're touching our toes, we're doing a gentle warm up before the perhaps tougher workout that will be coming our way later today. We, I guess, are all used to using really big data sets in this era of big data. We're using large data sets often that other people have collected painstakingly over many years, sometimes even centuries. And so we're having to rely to a great extent on the quality and the integrity of those data sets that others have created for us. And the key message from today's lecture is that attention to detail really matters. We have to be acutely aware of all the ways in which errors and biases can creep into the climatic data that we use on a day-to-day basis. And as I've already mentioned, that is increasingly important as we become more divorced, more remote from the actual collection of the data sets that we're often using. So if you take away just one message from this morning, it is treat every data set with a healthy degree of skepticism and be aware of the possibility of errors and biases within those data, which could affect the results. And I start with this classic example from 1999, when the Mars Climate Orbiter smashed into the surface of Mars. And the destruction of that satellite essentially wasted over $300 million worth of technology. How could that possibly have happened? How could a satellite end up crashing into Mars? Well, the simple answer was that the modelers who were simulating the trajectory, the orbit and the landing of the satellite were using metric units, and those who actually built the satellite were using old imperial units. So the mathematics of around the orbit and the landing just were calculated using two entirely different sets of units. And that's all it took to cost $300 million worth of technology. So even a unit error, whether we use inches, miles, or kilometers and meters, can sometimes have catastrophic consequences. So this morning, what we're going to be doing is looking at the hydromet information flow. I'm going to present this idea that data collection involves a sequence of events, and we need to be aware of the ways in which errors can creep into that information flow at various points along the way. So what are the telltale signs of errors and biases? How can we detect them, and how might we resolve these errors? And this is all happening before we even begin to analyze the data and to build our models to look for changes in the environment. So this is really preliminary work that we should all be mindful of in any study involving hydroclimatic information. So first of all, I'd just like to ask, and you might just wave your hands if the answer is yes. How many of you have had direct experience of working at a weather station or collecting field data? So how many of you have been into the field and, for example, taken a rainfall measurement from a rain gauge? Anyone done that? Okay, one or two. Yeah, rainfall and temperature measurements are, as I'd say, the bread and butter of our research. And as we will see later on, even those simplest of quantities can have all sorts of errors within them. So let's start with the hydromet information flow, which is laid out in this diagram for you. Now, as I go through the talks and the exercises, you'll see in the slides and in your handouts these blue links, these sources, which are all hyperlinked. And hopefully each one you can just, if you're interested, you can click on that link and it will take you directly to the research paper, report, or document. Okay, so just keep that in mind. So here's the hydromet information flow in its entirety. And I'm drawing here from a big review paper that I led a few years ago to look at all the different ways in which errors and biases can creep into hydromet data. And you can see that there's about 7 different steps which we're going to walk through over the next hour or so, beginning with what's the purpose of the data collection? How do we decide where to undertake the measurements? What are the instruments that we need to measure the quantities of interest? How do observer biases affect the measurements that we take? What post-processing happens and what sorts of errors can creep into very large data archives before we are finally accessing these data sets and using them in our research? So let's start with objectives. Many hydromet networks were set up for one of these 4 reasons. So firstly, we might be setting up a network to assess the available water resources in a river catchment or region. Essentially the water balance, how much river flow, how much rainfall, how much groundwater do we have? Secondly, we might be collecting data for the design of infrastructure. Just excuse me a second. Oops. There we go. That's a whistling radiator. So we might be collecting data on extremes like floods and droughts, very intense rainfall events, and these are used to design key pieces of infrastructure. We might be collecting data to check that water companies and industry is complying with environmental standards. So that's especially the case for water quality data. Or we might be gathering information to monitor how the environment is changing, either very slowly because of climate or because of direct human interventions such as land use change. But essentially, many of these aspects can be monitored through attention to just 3 or 4 quantities: the amount of river flow, the amount of rainfall, evaporation, and changes in storage, which may be, for example, related to groundwater or storage behind reservoirs. But essentially, those objectives set out the design of the observing network, the frequency of sampling, the types of variable that we're seeking to monitor through time. And here, for example, are the types of objectives that I've come across through my research in Tajikistan. So we might be measuring the amount of water in storage behind a reservoir to operate it safely. We might be measuring moisture levels in hill slopes to predict landslides. We might be monitoring water quality to assess compliance and to protect the aquatic environment. We might be monitoring heavy rainfall from space to predict flash floods, landslides, and other hazards. We might be monitoring glaciers to see how the mass of the glacier is changing through time, or we might be collecting data to design a safety spillway for a reservoir to enable that reservoir to operate safely. So with those objectives in mind, the key question is, where do we site the observing stations to gather the data that we need? Of course, governments and research laboratories around the world have finite resources, so we can't measure everywhere all of the time. So we have to make smart choices about where to gather the information we need to achieve the objectives of the observing network. We also have to ensure that the sites that we select comply with international standards for data quality, and perhaps the most widely adopted would be those issued by the World Meteorological Organization, where they set out the basic criteria for a well-managed meteorological station. So many of these points on the list here are obvious when you think about them. So the site's got to be secure, so equipment is not interfered with or stolen. It has to be maintained, protected from trash, away from high vegetation, which can affect rainfall measurements, no artificial heat sources. The site should be representative of the general environment in which it's situated, needs a good power supply, needs to be on level ground, and hopefully a place that's going to remain much the same for a long period of time, especially if we're trying to monitor environmental change. We don't want any other artificial influences coming into play. And also safe from natural hazards. And as we'll see shortly, that's sometimes quite difficult to do when we're monitoring extreme events in very active environments. So here we go. Here's the weather station compound at Loughborough University. So I actually did my PhD research, or part of it, on this site in the 1980s and 1990s, so a long time ago, and it didn't look like that then. If you look at this site, can anyone tell me, you know, does this look like a well-managed site? Is it complying with those WMO standards? And here I just invite anyone to switch on your microphone and just tell me what you think about what you can see here.
Slobodno kažete. Da li mislite da je standardno svetskim organizaciji? In English and speak up.
Raise your voice.
The green stuff.
The green stuff. So what we can see here is obviously some tall trees around the compound. So they would interfere with things like wind speed measurement and to a certain extent rainfall measurement. You can also see bushes that are growing nearby, which could affect rainfall measurements and others. But also when we see a site that looks like this, that looks a bit untidy and uncared for, that should be ringing alarm bells, because it says, well, you know, how much attention are people paying to the accuracy of the measurements at this site as well? It can be a signal of deeper issues. And I'm happy to say that our weather station doesn't look like this anymore. It's much, much tidier and really complies with the WMO standards now. Okay, what about this one? This is taken from a paper by Roger Pilkey and others, and this is on the recommended reading list, in which the authors traveled all over the US and took photographs of sites in the observing network to just highlight how errors can creep in. So any thoughts on this one?
This is nonsense.
Why don't you like it, Manfred?
Because the house, I see the effects of the house, but not of the weather, or not so much of the weather.
Yeah, absolutely. So what we can see here is the thermistor, the temperature monitoring device. It's obviously going to be affected by radiant heat from the wall and heat from the air conditioning unit as well. So obviously the temperature measurements that are being submitted by this observer are meaningless, but you would be surprised at how many stations are like this across the US and were identified in this this survey. Okay, one more. What about this one? This is the weather station in Athens as it was in the mid-1980s. So you can see in the left-hand side the Acropolis. What do we think about this one? Well, okay, well, perhaps this is a trickier one, because straight away you can see that the measurements are occurring on the top of a tower above vegetation. So they're not at all of the measurements, none of them are being undertaken at ground level and at a standard height. So it might seem an obvious thing, but around the world, the Met Office wants us to be undertaking temperature measurements at somewhere between 1.5 and 2 meters above the ground. You can also see the weather, the wind vane at the top, which is going to be measuring wind speeds at different heights, no doubt also not at the standard level. But unless you'd actually been to the site and looked at them, we could quite happily be using data gathered from Athens in our trend analysis, our modeling, and just how representative is this essentially green site of conditions within Athens as a whole. These are the sorts of skeptical questions we need to keep in our mind as we're analyzing these kinds of data sets. Okay, now let's just think about more generally where sites are. And across the world, when we look at meteorological data that we can generally access, much of it has come from close to sea level, on the edge of large cities and at airports. And we have relatively little information at critical sites like high altitude locations, headwaters of major river basins, which are really driving much of the downstream hydrological change that we're interested in. And globally, there's just remarkably few sites where we're measuring weather above 5,000 meters. Now, later on, you'll be in this course, you'll be hearing from Tom Matthews, and he's been doing great work by installing a weather station near the summit of Mount Everest. Now, that's quite an extreme case and environment to gather data in, but if you look at this chart here, it shows two important things. So the dotted line here that I'm highlighting shows the distribution of snow and ice in the Himalayas. So you can see that the bulk of the snow and ice is sitting at around 5,000 meters above sea level. This is the elevation along the bottom here, about 5,000 meters. And the solid red line here is showing where the monitoring stations are in the region. So you can see the vast majority of the stations are, as I said, at sea level. So we're measuring, in this case, conditions that aren't really telling us much about what's happening in these great water towers feeding some of the largest rivers in the world. And we have so few values here that we're essentially operating in ignorance in terms of how those water towers might be changing through time. Our basic observing network is essentially biased to very low elevation sites and is giving us information, in this case, that isn't particularly relevant to some of the most important hydrological changes that are happening on the planet. Here's another example that I came across when I was working in Yemen about 10 years ago. And what you can see on the left-hand side is a map of Sana'a city, which is an incredible city surrounded on three sides by high mountains, jagged rocks. It's like an amphitheater. And we can see during one particular summer, the local university undertook rainfall measurements at 4 locations in and around the city, spanning about a 10 kilometer difference in space. And on the right hand side, you can see the amount of rainfall that was accumulated over that single summer. And interestingly, these two sites that are neighboring are the ones that are giving the most extreme difference in the rainfall. So in one case, one site is giving nearly 200 millimeters, and the other one is giving less than 100. So here, in the space of less than 4 kilometers, there's twice as much rainfall in one location as another. So again, this raises questions about how many stations do we need to accurately measure rainfall across this critical basin, which is the most representative site that's measuring rainfall across this network. Again, these are the kinds of questions we need to keep in mind. How representative are the sites that we're using in our analyses of the variability in space and time over larger domains? Okay, does anyone have any questions at this point? I'm not sure if I can access the question list. Does anyone have any questions? Biljana, are you able to read any for me?
There are some, not questions, but some statements when they answer the questions that you asked about Athens, I think, measuring station. You can see it in the chat.
Okay. All right.
Yeah.
All right. Well, let's continue then. So let's think about some of the other things that can affect basic hydrometeorological variables. And perhaps one of the best known ones is the growth of cities and how they can affect temperature records. So we might have, as in the case of Beijing, established a weather station in the 1950s in a site that was essentially rural. Then over the decades, the cities have grown and have grown around the rural site. So you've replaced a weather station that was measuring rural conditions with one that is now measuring essentially a peri-urban or an urban climate. And so there are a range of techniques that we can apply to strip out that urbanization effect from the temperature trend. For example, by comparing temperatures on windy or non-windy days, we can eliminate the urban heat island. But this is a very important and common source of contamination of temperature records that we should keep in mind. Also, many of our rivers over years and decades have been subjected to groundwater abstraction or direct abstraction from the surface water. And here's an example of a river in the south of England, where we see in the red line the amount of river flow in the summer through time. And the blue line shows what the flow would have been had there been no groundwater abstraction. So we've reconstructed the river flow series to show what would be there under natural conditions. And so straight away we can see that there's a very large difference between what is observed in the river flow and what has been occurring or would have occurred naturally over this same period. And actually, very few records worldwide are naturalized, in the sense that the water that's been taken out by us, by people, is added back to the river flow to give this naturalized sequence. So often we're working with river flow records that are, again, contaminated by these types of artificial influence. There could also be big changes going on within the river catchment itself. Removal of forests or replanting of forests, or in this case, improving upland drainage. So this is a picture of a river catchment in Ireland, where in the 1970s, extensive drainage networks were installed to reduce the amount of waterlogging and improve the quality of the land for agriculture. And as you can see here, if we just look at the black line, there was a major jump in the variability of the flows in the post-1970s period. And that is a reflection of both the land use change in terms of the drainage and a change in the rainfall regime. So in this case, there's two factors at play: a natural factor from the rainfall and an artificial factor, which have combined to affect the peak flows in this particular river. And I'll be coming back to this example later again to explain how we can arrive at that kind of conclusion. And perhaps one of the most widespread influences on river flows is, of course, river regulation by large dams upstream. And these types of structures can significantly change the river flow regime. Again, if we look at these rivers in Central Asia and Tajikistan as an example, the blue line shows the natural flow regime in the 1950s that existed before the dams were constructed. And then more recently, we see in the green line how, with the operation of the hydropower systems, there's been a shift to a complete reversal of the natural flow regime. So the peak flows are now occurring in the winter time as water is released to generate hydroelectric power. And that compares with the natural flow regime, where the peak was in the summer because of snow and ice melt. So here's a very extreme case where the actual flow regime has been essentially reversed by the operation of an upstream hydropower plant. Okay, so that gives you a sense of some of the issues around the selection of site and some of the artificial influences from sites. Now let's just move into a little bit more detail on the nature of the instruments and the monitoring that we're doing as well. And here we need to be mindful of how changes in the type of instrument, their calibration, the condition of the instruments, and the accuracy of measurements might change through time. So here on the right-hand side, you can see quite an extreme case where this river flow record shifts from manual measurements, where someone has gone and stood in the river with a flow meter, measured the cross-sectional area of the channel, and calculated the amount of river flow, through to, in the red period, installing a fixed structure, a weir, that then automatically measures the river flow through time. Now, comparing the blue with the red, we don't know whether the change in the flow regime here is due to the shift from the manual to the automatic monitoring, or is perhaps reflecting an actual change in the environment, perhaps a wetter period with higher and more variable river flows in later decades. Point is that that change in the instrumentation has affected our ability to attribute or explain a change that we can see in this particular time series. And this is why the standardization of instruments is so important. And I just flag up here that, for example, in the UK, the rain gauge was standardized in about the 1860s. So we've got about 150 years of rainfall data where we've been using the same kind of rain gauge design to measure rainfall all across the country, rather than, as in this old graphic, showing how some people use different shapes and sizes of rain gauge, some on rooftops, some attached to chimneys, some on ground level, some in open or closed spaces. And you can imagine, with all that variety, we're not really in a good place for comparing rainfall records between different locations or over time. And in fact, when we consider the lack of standardization in the early 19th century in the rainfall record of the UK, we can discern some really big biases in the data sets. And in fact, during the particularly cold era of the early 19th century, some of which some people refer to this period as the Little Ice Age, the winters were much colder and had there much more snow. And because the rain gauges weren't very well designed, the amount of snowfall was not measured accurately in these early decades. So if we just looked at the data set without knowing that, we would say, well, there's been a significant increase in rainfall through time. And that increase is purely an artifact of our poor measurements at the start of the record, our inability to measure snowfall in early decades. And sometimes we also need to take into account the housing, the classic Stevenson screen that we can see here, which contains important instruments, especially thermometers, in a shaded environment. If those thermometers are not shaded, as we can see on the left-hand side for the site in Madrid, we get much, much higher temperatures than if they are properly shaded within a Stevenson screen. So the differences between these two records in the early decades is because one instrument was shaded and another one wasn't. Also, the Stevenson screen, as you can see, it should be pure white to reflect solar radiation and keep the box inside as cool and at a constant temperature. But as the Stevenson screens age, they get dirty, they change color, and that affects the temperature record inside in quite subtle ways too. So even the color of the paint on the Stevenson screen can be a factor affecting the temperature measurements inside. And then when we think about river flows, one of the most common way of estimating river flow is to relate the depth of flow shown on the horizontal axis to a logarithm of the measured amount of flow. So this might be measured manually in all sorts of ways. And if we're lucky, we'll have this nice semi-linear relationship. So as the depth of flow increases, so our estimate of discharge increases. But if we go to the right-hand side and we go back to this particular site at different periods in time and try to construct the same relationship between the depth of flow and the volume of flow, we can see very different curves, very different relationships at different periods. And this is because the channel cross-section has changed. It's not fixed, it's not concrete, it's a dynamic part of the environment. So sometimes there's vegetation, sometimes there's erosion, sometimes there's deposition of sediments in that channel, which affects the relationship between the height of the water in the channel and the assessed flow of water in the channel. So we can't even assume that discharge measurements based on these kinds of techniques, which are pretty common around the world, are stable through time. As we can see, different curves representing different rating relationships, reflecting changes in channel conditions through time. And even from space, as we increasingly now rely on remotely sensed rainfall information to feed into our models and our research, we look down from space, and there are many studies which have tried to look at the accuracy of spaceborne rainfall estimates with ground-based measurements. And here's an example from a study in Kyrgyzstan, again, Central Asia, showing locations where the correlation between the amount of rainfall measured from space and the amount measured on ground is very, very weak. These are shown in the red. In the black is where we have much stronger correlations. And what we learn is that the sites that are red are where there's nearby water or a lake, a water body that affects the signal that's being measured on the ground. Or there might be problems associated with the complexity of the topography. So generally speaking, rainfall measurements from space are problematic in areas with complex terrain, snow and ice and water bodies on the ground. So there are differences in our ability to measure rainfall from space depending on the properties of the ground. And here's one of my, again, sort of favorite photograph of a rain gauge that I photographed near the summit of Mount Vesuvius in Italy. So I look at that that rain gauge and I can't help but smile. It's a beautiful object. It's been decorated obviously by lots of visitors to the volcano. But when I look at this, I just think, how reliable are the rainfall measurements at this site? What's the likelihood that someone has interfered with the rain gauge in some way, even perhaps pouring some water in from a drinking bottle or something just for a joke? These are the sorts of things we need to be mindful of. So how trustworthy might that rainfall record be? I honestly don't know, but when I see an instrument like this, it raises all sorts of questions in my mind, just like that. So a question for you now then, if we are measuring the amount of water behind a dam in a reservoir, and we're using a height stick like this with the graduation here, any ideas on the types of error that we might have in this situation in terms of estimating the depth of the water and hence the volume in storage? Here again, I invite you to make a suggestion. Any thoughts?
The reservoir itself, it is under the influence of the dam. So when you use the dam, the water level have to change. So it's actually water level that you are actually measuring the water level done by humans, not naturally.
That's it. So, well, we've got the water level obviously reflects the operations of the dam, exactly as you've said. So if water is being released for hydropower, that affects the water level. But here there are subtle problems, because I might come to this dam to look at the measuring stick on a day when it's really lovely and still. And so the water surface is like glass, and I can get a very nice measurement against this stick. But I might come back the next day and it's very windy and stormy, and so there are big waves coming across the reservoir lake, affecting the measurements up and down here. So what measurement should I take on a windy day to reflect the storage in this site? Or because it has to be done manually, I might be on holiday one day or unable to get to the site to take the manual measurement. So in which case a measurement is missing. You can just see how some of these just very simple factors can have quite a big impact on what would be the measured height in this reservoir, and hence our estimate of the river flow. Sorry, of the amount of water in storage. Okay, you've been listening to me very patiently. I suggest we just take a 5-minute break here to stretch our legs and have some coffee. Biljana, are there any questions or comments that we might just touch?
Yes, there is one question in the chat. If you can open the chat, or I can read it for you.
It might be easier if you can read it for me. Thank you.
Okay, here it goes. Is there some studies that prove with non-artificial methods such as tree rings theory that little ice age was less intensive that we conclude from the artificial data?
So sorry, it's a question about the little ice age and yes, how significant it was. Yes.
No, it's about non-artificial methods such as tree rings that prove that the little ice age was less intensive that we conclude from the artificial data. I'm not really sure what artificial data is, but maybe Rasko can explain. Could you please explain, Rasko, what you meant?
You said that little ice age was less intensive because you said we concluded that it was much more intensive because we didn't have standards for those how to say gauges. Yes. Okay. So is there some studies that proves that we got some bad conclusions because of not having a good standard in that time?
Okay, I think I understand the question. So yeah, a lot of the evidence for the little ice age comes from tree rings, and I think that's what you would call an artificial source. So it's you know, measuring the thickness of a tree ring or measuring the amount of isotopes in a tree ring to reconstruct temperatures through time. So there's a lot of information collected around the planet to measure the extent and the severity of the little ice age.
There's some comparison to that early 19th century data that people collected from man-made gorges. There's some comparison to the tree rings data.
Yeah, so there are studies where people have done that, where they've tried to compare those early records that have been collected manually with long tree ring records. And if you're interested, just send me an email and I can share some sources with you that you might like to read. I mean, the interesting thing about the little ice age was that people have talked about how extensive was it? Was it essentially Northwest Europe, or was it much larger than that? Was it the whole of the Northern Hemisphere? How much of the planet did the Little Ice Age affect? And so there's a lot of discussion about whether it was a local ice age, little mini ice age, or whether it was much more extensive. But if you send me an email, I can send you some example papers.
Okay, thank you.
All right, shall we take a 5-minute break? We'll come back at 9:55 and continue with some of these other issues.
Yeah, that's fine. Yeah, I hope everyone agrees. Okay, see you in 5.
Okay. Okay, welcome back, everyone. Now I'd like to let's see, move on a slide. I'd like to concentrate on the human factors that can really introduce all sorts of strange biases into our data. And hopefully some of the examples I'm going to give you are both surprising and new ideas to you, things that you might not have thought of before. So we kind of assume that someone who's been trained in the use of meteorological data and equipment would undertake the measurements in consistent ways. And so any two observers should produce the same temperature or rainfall measurement. And as I'm going to show you, that is certainly not the case. And this is a major source of uncertainty within the hydrometric information flow. So here again, a question for you. Let's look at the automatic weather station on the left, installed on a relatively high altitude glacier. What sorts of things do you think could go wrong in this case? Any ideas?
Slobodno kažite.
I'm not sure I caught that, but let me just say that for here in this case, obviously there could be loss of power supply. The automatic weather station is depending upon solar cells to recharge the batteries, so those can run down. There can be hazards to the equipment from avalanches and rock falls damaging it. It can be very difficult to reach these sorts of sites to replace and repair equipment under certain conditions. And in the case of glaciers, when we're installing a weather station on a glacier, that is actually moving as well. So the station position could be changing through time unless it's fixed to a secure margin. On the right-hand side, we can see a widely used device called a tiny tag, shown in the yellow, and this is used to monitor air and water temperature. And it's essentially a thermistor which you install in the location, and you can come back many months later and download the data. But of course, if we're installing a thermistor in this sort of environment, the river can change, the equipment can be buried by sediments, rocks can damage the instruments, or the river flow can drop, so the thermistor is exposed to the air. So we're measuring air temperature rather than water temperature. Or the thermistor can be exposed to direct sunlight, so that artificially warms the instrument as well. Lots can go wrong, even in simple measurements like water temperature. And in the case of rainfall measurements, these are particularly problematic when undertaken manually. So there are a variety of ways in which we can measure rainfall manually. And in the US, on the right-hand side, the most common way is to essentially place this dipstick into the rain gauge and look at a scale to see where the water level is. And just to give you an example of how little errors can have big consequences, if with that manual measurement we are making a mistake of just 0.1 millimeter over a river basin the size of the Thames feeding through London, that can equate to 1 million cubic meters of water that you've got wrong as a water company. So you've either gained or lost 1 million cubic meters of water based on every 0.1 millimeter error in a catchment that size. And that's a catchment of about 10,000 square kilometers. So imagine the errors that you could accumulate over a catchment the size of the Danube, where little rainfall errors really matter when scaled up over such a vast area. Now, also, humans have a natural tendency for certain numbers. We tend to like numbers that are divisible by 5 or 10. So here, if we look on the left-hand side as a temperature record, we can see large spikes in the frequency of certain types of measurements. So this is the daily maximum record here, and this is the histogram showing the frequency. So you can see that whole numbers like 5, 10, 12, 20 have much higher values than the numbers in between. So we like whole numbers like 12 degrees Celsius much more than we do 12.1 degrees Celsius. And this number bias is seen all over the world. I've seen it in many different locations. So that's quite common in temperature. In rainfall, as in this example, we can see preferences for rainfall measurements, again, are divisible by 5 or 10. So we see more frequent counts of 5 millimeters, 10 millimeters, 30, 25, and so forth. Much more common, and very few measurements in between. Also, we have to sometimes check that the date keeping of the record is right. In this particular one, there were data values entered for 30th and 31st of February 1995. So what does that say you? I mean, how can we trust those numbers as a whole if there are imagined dates within this particular record? And another rather unusual law that we see is called Benford's law. Now, in nature, we expect the numbers beginning with 1 to be much more common than numbers beginning with 9. So in fact, and this applies in all sorts of natural environments, the number 1 should be occurring about 30% of the time as the leading digit, and the 9 about 5% of the time. Not evenly, not a 9th or a 10th in each of the numbers that you'd expect. So where we see a departure from that natural law, that can again be a signal of some human influence or bias in the data. And in fact, one analysis of rainfall records in the US found that very few of them actually passed the 510 bias test. So every rainfall station in this network that is colored red has a 510 number bias. So the observers are showing a preference for certain types of number and avoiding others. Other sorts of bias are the so-called Sunday effect. So in the US and Australia and in the UK, when people are taking Sunday as a day of rest, they're less inclined to go to the weather station and take a measurement. So you can see, for example, in this study, there's lots of missing days on the weekend. And that has an effect on the number of rain days that we're measuring. And then downstream, all the rainfall statistics that we're estimating. So this so-called Sunday effect, or day of week bias, is something, again, that we see in many types of record around the world. And it's particularly important if we're interested in, for example, extreme rainfall amounts, because you can find that if someone hasn't taken a measurement on the Sunday, they might come on the Monday and bulk group together the 2 days of rainfall, and you end up with a record, a value that is much higher than it should be, because you've combined 2 days of data. So the Sunday effect is a very common phenomenon, one that we should, again, be mindful of. Another problem is inconsistent measurement time. And here is one of my favorite examples, again, taken from the UK water temperature measuring network. And it shows the time at which the field officer went to the river and took the spot measurement of the river temperature value. So you can see in the 1990s, the technician was typically going to the site at about 9 o'clock in the morning. And then 15 years later, the field officer was typically going there at about 1 in the afternoon. So think of it in terms of a breakfast measurement here and a lunchtime measurement here. So obviously, water temperatures are likely to be warmer at lunchtime than they are at breakfast time. So this drift through time towards later in the day measurement actually has an impact on our estimate of the amount of warming in this river. And it actually, just that gentle drift by 3 or 4 hours of the water temperature measurement has increased the rate of warming inferred for this river by 25%, just from the drift in the sampling time. Okay, now we just move to sort of the closing stages, and we start to think about some of the typical errors that can occur within archives and the post-processing of data. And one thing I'm always encouraging my own students to do is to just simply plot the data and visually inspect them. That can help pick up so many problems. Here, for example, if we're plotting temperature values at this particular site, straight away we can see, well, do I believe that there's an air temperature of 60 or 70 degrees Celsius? Almost certainly not. Well, we're not going to be measuring an air temperature that high, but when we've plotted it graphically like this, it becomes very apparent. Likewise, we might see a large number of zeros where someone has used the value 0 to represent missing data rather than an actual 0 temperature. And again, that's a very common error that we see in data sets, the use of 0 to represent missing data. So when we're visually inspecting data and we see outliers and spikes, we have to ask ourselves all sorts of questions. Are those spikes spurious or curious, as I say? So here's an example where we can see spikes that are actually real. You know, we look at this record here and we think, well, what's going on here? Is this a problem or not? It's not a problem, because in this particular case, we're seeing the activity of crayfish within the river system, stirring up the sediment and increasing the turbidity. So there's it's the natural ecosystem, the biota, that are producing these spikes in the data, and we can see this observed in both the laboratory and in the real world. So looking at the data set, thinking about, are there possible explanations for these outliers, or are they just simply an error? So having some hypothesis to explain why the outliers exist is always a good thing. And the use and misuse of outliers has many famous examples. You know, outliers can be used to produce all sorts of spurious trends in data. And perhaps Manfred will be saying something about this later. I will certainly later on. And perhaps one of the most famous uses of or selective use of data was the so-called global warming pause, where skeptics of climate change were able to pick pieces of temperature record which showed apparently no change. Of course, they in this particular analysis, it doesn't include the most recent 2 or 3 years, which were record high temperatures, which even within this short section of data would produce a trend. But the selective use of data, subsetting data, or the selective use of outliers, or the influence of outliers on data, can introduce all sorts of spurious trends and inferences. And then within the archive itself, I've already mentioned lots of things that can go wrong. We can have missing days, particularly leap years, where the 29th of February has been missed, and then all the days are incorrectly coded. We can often see keystroke errors when data have been manually entered, or there's been a switch between units, decimalization, for example. There are many sources of error, and as I mentioned before, if you go and look at this review paper that we produce, you can see just how common and how varied these types of errors are, which, if you don't inspect the data, you might not be at all aware of. Again, the analysis of trends is very sensitive to the record start and end date in relation to the variability within the section of data, as illustrated by these two periods of temperature record. I can arrive at very different conclusions based on these data, depending upon which section of the data I choose to use and its relation to outliers, whether at the beginning or the end of the data set. And we have to be mindful of the fact that there can be more systemic errors within the archive as a whole that reflect an evolving network density through time. So if we look at here, for example, the growth of the rainfall monitoring network in the UK from the 1960s, reaching a peak in the early 2000s and then declining. So we have fewer gauges, the network has changed in terms of its distribution and the number. And we can also see in terms of daily rain gauges, much more marked and abrupt changes here, which affect our estimates of aerial rainfall through time. So if we're not correcting estimates for changes in the number and the distribution of the gauges through time, that can lead to false conclusions about changes in some of the extremes, some of the area averages, depending upon the sampling in space and time. Okay, now some questions for you to just see if you can spot the errors. Let's start with station A. Can anyone tell me what the error might be here, just by visual inspection? So, anything wrong with this record, which is a daily river flow record, station A?
There's a missing gap between 80s and 90s.
So we're talking about this area here? Yes, so you can see here, at this particular station, for some reason, they decided to use a missing data code of 199. So, and unfortunately, 199 is within the range of the observed data. So if we hadn't visually inspected it and looked at this, we could have quite easily used those data and included a missing data code as an actual data value. Okay. All right. What about station B? What's the problem here?
Data are full numbers without digits.
Yeah. So we can see for values less than 1, we've got all sorts of values between essentially 0 and 1. Okay, so it's a continuous scale. Whereas for values above 1, it becomes essentially a category scale. So we don't have any values between 1 and 2, and no values between 2 and 3. So for some reason, the data shifts from being continuous to a categorical scale in this particular record. This one is quite obvious, so I won't insult your intelligence by asking you what's wrong here. But when we see something like this is often an example of a decimalization error. So here, the decimal place is situated in the wrong position in the number, and so it's making it a tenth too small. What about this one then? Station D. Can we see any errors there? Okay, well, here we can see some numbers that are 0. It's again that quite common error where a missing data value has been given a value of 0. And you can see a few instances where one might think that there is no river flow in this location because the value is set to 0, but it's actually a missing data value within the record. So you can see all sorts of very subtle errors here that could influence our design estimate, our water balance calculation, and our trend assessment. So one of the key take-home messages from this morning is to always, where possible, refer to the metadata that accompany your data set. So it might take all sorts of shapes and sizes. The metadata might have a nice map of the location where the data were gathered. It might have handwritten logs which describe some of the problems encountered at the site, or it might even help us to see when there was a change in the observer, one name here, a different name here, or it might help us to spot that the weather station was moved from one location to another, or changes in instrumentation. So metadata is really, really important to refer to as a key task when we're using someone else's data that we haven't collected ourselves. So just to sort of bring us to a conclusion here are some of the sources of data error that we might typically come across within hydrometric archives. And I've shown you examples of these this morning. So where there's been a change of instrument, where the sensor has been damaged or moved, there can be problems to do with the gradual drift away of accuracy, particularly in temperature, if we haven't recalibrated the instruments. Different observers prefer different numbers. Some of us like 5s and 10s more than others, or some of us are reluctant to go and take a measurement on a Sunday, or there are all sorts of other issues around the observer. How representative is the sampling location? Has it changed in position? Has it moved to a higher location? That could affect the rainfall measurement. As I showed you with the temperature in the river, sampling times can drift over time as well, or there can be a whole host of artificial influences going on within the river basin, from urbanisation, river regulation, and so forth. And then what do we do about missing data? How do we codify that? Do we use a meme to fill in the data, or do we interpolate? There are lots of different techniques for building a complete record, and if these aren't stated clearly in the metadata, that can confuse a user later on. And then there's simple human errors as we're typing data from data sheets into the archive. Keystroke errors can occur and so forth, or there can be a change of unit. So I really want to stress the importance of visually inspecting data wherever you can. And sometimes when we're working with vast archives, we can visually inspect data by producing maps or aggregate values, or looking at outliers. But this is a really important step that we should go through before undertaking the in-depth analysis of the data. And this is again a key take-home message from this morning, is that myself, and I guess many of you, will be increasingly relying upon data sets that other people have collected. And we're increasingly in this era of big data, using large archives of information, where we become detached from the realities of the actual data collection on the ground. So when we have such large data sets, the types of error and bias that I've explained to you can just be lost. They can be like a needle in a haystack, like the numbers here, the V, the I, and the X within this cloud. You can spot, 3 red symbols in there that I've hidden in the mess, which could be the erroneous data. And this applies not just to observational data sets. You can, when you take a very careful look at reanalyses, these quasi-observational data sets may also contain subtle biases or archiving errors that without careful inspection and interrogation can lead us to quite wrong conclusions about the patterns of change within the data set. And this really is a particular issue, I'd say, for our generation now, because we increasingly rely upon the data that others have collected for us. There are fewer and fewer of us who are actually physically going into the field to collect the data that we are going to use in our own research. So I think that's probably a good point at which to wrap up.